Hello everyone and welcome to this presentation concerning refractory development frameworks using computational modeling. My name is Nathan Daubenmeier and this presentation is a result of an undergraduate internship that I had with the National Aeronautics and Space Administration as well as a partnership with The Ohio State University. I'd like to mention Antonio Ramirez from OSU as well as Frederick Michaels, Jeffrey Soward, and Omar Mireles from NASA. Thank you for your assistance in this project. This presentation will be discussing using computational modeling in order to estimate solid-state cracking and solidification cracking of refractory alloys. A little bit about me. My name is Nathan Daubenmeier, and I am currently an undergraduate student in a BS/MS program between the Mechanical Engineering and Welding Engineering departments at The Ohio State University. I plan on transitioning to a PhD student once I finish the BS/MS portion of my classes. A few CV highlights. I was an undergraduate research assistant with the Welding Engineering Department here at OSU for about 2.5 years before I took an internship with NASA for the summer. The internship was concerning computational modeling of engineering alloys for spaceflight applications, and that internship is what led to this presentation today. I am currently a graduate research associate at OSU working with the Welding Engineering Department, and my contact information is listed there if you would like to contact me about this presentation. So some of the motivation for computational modeling is, particularly with refractory alloys, is due to the high cost of the material and the difficulty that it can be to produce the refractory alloys. This can limit wide-scale investigation into compositional spaces, making it difficult to get really specific material properties from the alloys. Computational modeling allows for a low-cost solution to analyze a wide compositional range very efficiently. We have preliminary results of some of the programs we've been writing where we are calculating around 300 alloys per hour. This speed allows us to brute force calculations over a wide compositional range and analyze all the material properties for each of those compositions. This allows us to really tailor the elements and the ratio of all the elements that are going into these alloys in order to get the best material properties. Since this is an initial dive into the refractory space using computational modeling, we were primarily focused on zirconium, molybdenum, tungsten, and rhenium as our primary elements, and we also looked at carbon and silicon for other alloying elements. There are other important elements to look at here, but this is where we will be focusing on in today's presentation. So Calfade-based software has undergone a lot of development over the past several years, and one development was within the property model that thermocalc uses in order to calculate different material properties. So recent updates has enabled the calculation of several physical characteristics of alloys, including solidification cracking susceptibility coefficient, which is a model that estimates the solidification cracking tendency of a material composition during solidification, as well as a yield strength property, which includes a model for calculating yield stress determined by the total of a combination of strengthening mechanisms, including precipitation, solid solution, grain boundary, etc. The yield strength can provide information about solid state cracking because it can help. We were hoping that it would help us to estimate the ductile brittle transition temperature. But the point of using Calfade-based software is that it provides rapid capability that allows us to model and predict thermodynamic and physical properties of novel alloys, as well as characterizing in more detail existing alloys. We also used Python in order to interface with the thermodynamic software. This enabled us to do high throughput simulations to achieve the calculation speeds that I mentioned earlier, and two of the primary models that we used through Python was the Scheil solidification curves and single equilibrium calculations. So the Scheil solidification model provides a lot of information that we can use to understand the alloy's solidification under actual processing conditions. So a few key parameters that we pull from the Scheil solidification curves include the solidification temperature range, as well as the liquidus and solidus temperatures, solidification sequence, and then an initial look at crack susceptibility. So Cohen-Leo's model is a common model that has some limited application to crack susceptibility, primarily with aluminum alloys. And I'll discuss later in the future work section some of the work that we are doing in order to try to adapt this model and make it system agnostic so that it can apply to a broader range of material systems. For the single equilibrium calculations, they can also provide some information on the partition coefficient and the liquidus slope, both of which can help to provide an understanding of how the elements are moving around within the material, which can be helpful when we're looking at solidification cracking. To start off with, we wanted to compare CalFAD calculation of phase diagrams results versus literature results. So on the right here, we have a tungsten rhenium binary phase diagram that was produced through the use of CalFAD software. And then on the left, we have the literature version of the tungsten rhenium binary phase diagram. As you can see, there was good similarity between these two diagrams, providing confidence that the thermodynamic software is modeling the system well, and the database that we're using as well is very important. So for the solid state cracking, one major issue with the use of refractory alloys is that they tend to have a limited ductility due to the large grain size, grain boundary embrittlement from oxygen, and a ductile brittle transition temperature that is well above room temperature. So if we could calculate where the ductile brittle transition temperature is and alloy it with various elements, or model alloying it with various elements to see which of those elements help reduce the ductile brittle transition temperature and reduce the solid state cracking, that would be beneficial. Unfortunately, the ductile brittle transition temperature cannot be calculated directly from CalFAD, so a few other methods were investigated to provide insight into ductility. These were yield strength versus ultimate tensile strength, hardness, and elongation percent using Gibbs and Helmholtz free energy. The yield strength and hardness were two factors that we hoped to get out of CalFAD, and the elongation percent we calculated using various equations that we found in literature. Looking at the yield strength, we were expecting to be able to enter a composition and a temperature and get out the yield strength at that temperature. The thermodynamic software that we were using provided the results shown in the figure on the top right, where we have temperature on one axis, the rhenium content on the other axis, so this is a tungsten rhenium binary system, and then the yield strength on the vertical axis. As you can see from the figure, there is a lot of range of temperature where the same yield strength is predicted. This goes counter to what we expected and what you see in literature, where in the literature graph you can see that with increasing temperature, the yield strength decreases. This makes sense for most materials. And because we were not seeing these results, we had to do a deeper investigation into how the thermodynamic software that we were using was calculating or was using the inputs that we were giving. So what we found out was that it treated the temperature that we were providing as a heat treatment temperature, essentially, and always providing the yield strength at room temperature. This is a limit of the software and the data that the software uses in order to provide calculations, and it's not something that could be easily overcome. And this meant that we were not going to be able to use yield strength in order to calculate the ductile brittle transition temperature as we hoped. We experienced a similar problem when we began to look at hardness using the CalFAD software. The figure on the right again shows a similar behavior as what we saw with the yield strength, where it has wide ranges of temperature where the same hardness value was predicted. From this, we hypothesized that thermocalc was using Tabor's relationship to calculate the hardness from the yield strength, where hardness is equal to 3 times the yield strength. And when we plotted this, we found that this was the case. So it was calculating hardness in a similar way that it was calculating yield strength, and this is not did not allow us to gain additional information about where the ductile brittle transition temperature was. Because of this, we moved on to the solidification cracking susceptibility. So another common issue when processing alloys like refractory alloys using common technologies like welding or additive manufacturing is solidification cracking. And so, as I mentioned earlier, Ko and Liu demonstrated using that model, using the maximum of the derivative of the Shao curve in order to estimate relative cracking susceptibility, solidification cracking susceptibility. They saw good application for aluminum alloys with limited application beyond those alloys. Despite this, we use this model in order to run a wide compositional range for a molybdenum zirconium carbon alloy system. And that is what is shown in the heat map on the right side of the screen. This heat map is color indexed by the cracking susceptibility, with zirconium on the x-axis and carbon on the y-axis, with molybdenum as the filler element. We use Python in order to calculate this wide range of compositional space. And the goal of this is that the map would show you areas of compositional space where you would likely have high solidification cracking susceptibility. This would then be able to fund your information in the lab when you're experimentally producing alloys of compositional spaces to avoid in order to avoid solidification cracking. Some of the future work that we've been working on in order to expand off of Ko and Liu's model is shown on the slide now. And the goal was to cover a broader spectrum of alloy systems, so they'd be system agnostic. This means that you'd be able to run the same calculation on an aluminum system or a steel system or a refractory alloy system and get out results relaying relative cracking susceptibility. So in order to develop this model, we use computational fluid dynamics in order to calculate the liquid backfilling resistance on a columnar grain profile. So in figure A, you can see two grains shown that are growing side by side. In order for these to solidify, liquid has to feed down into the space between the grains, and the resistance of the liquid to flowing down into the grains can relate to solidification cracking. So we added a viscosity variable as well as some other factors from CalFed into this equation, which is shown on the bottom right, that we have developed in order to estimate this solidification cracking susceptibility. On this slide, we show an example demonstrating the advantages of this newly developed solidification cracking index. So this was an iridium modified 7075 aluminum alloy, which both Klein and Davies index and Ku index modeled incorrectly. You can see in the top right that Klein and Davies index predicted increased susceptibility with the addition of this element, and Ko's index on the bottom left also indicated increased susceptibility with the addition of this element. On the bottom right, you can see that the newly developed OSU index estimated decreased susceptibility with the addition of this element, which is what was actually seen in experimental results. This shows some of the benefit of this system in incorporating the computational fluid dynamics. And there are other examples as well that we are working on to show the advantages of this cracking susceptibility index. The first publication of this index is out, and you can find it. Is titled New Composition-Based Technique for Solidification Cracking Resistance Evaluation. And a second publication is ongoing, where we are aiming to make it more accessible. So we're doing that by minimizing the need for computational fluid dynamic software so that it will be easily integrated with Excel, Python, or MATLAB or something like that. So it can match the ease of use of Ko and Liu's model. Some concluding remarks: computational modeling of alloy systems continues to demonstrate high capability for modeling physical material systems with much greater speed and lower cost. Refinement of refractory alloy spaces provides benefit for specialized flight applications, including nuclear thermal propulsion, green propulsion, and hypersonic flight. And the adaptation of computational models for different compositional spaces, energy inputs, and solidification rates promises rapid alloy development and refinement. Thank you for listening to my presentation, and feel free to reach out if you have any additional questions. Thank you.